It started quietly. No dramatic flare, no sudden discovery. Just the soft hum of a telescope motor, rotating toward coordinates logged the night before. February 3rd, 2026. A cool, dry morning across most of the northern hemisphere. In a small backyard on the outskirts of Flagstaff, Arizona, an amateur astronomer named Paul Craigs powered up his telescope. A dwarf 3-unit, compact but capable. He wasn't chasing anything extraordinary. His logbook showed the same entries as dozens of other nights. A fast-moving object known as 3I Colon Atlas and a rapidly growing sunspot group, designated AR4366. He aligned the scope. He waited for tracking lock, and then he took the shot. On the surface it looked routine, just another long exposure capture of a comet near the ecliptic plane. But when Paul opened the image in his processing suite and began stretching the contrast, something felt off. Comets are supposed to be messy, icy bodies that scatter light unevenly, throwing out clouds of dust and gas in the heat of solar proximity. What he saw wasn't chaos, it was structure. At the center of the image, a bright white object with crisp edges. Too crisp. A smooth halo wrapped around the body, not diffused like vapor, but tight, symmetrical. And behind it, a faint line of bluish light extended cleanly into space. No ragged coma, no dusty turbulence, just geometry. That wasn't the only surprise. The sunspot in the corner of the image, AR4366, looked active, aggressive. It had grown visibly since Paul's last session. NOAA had already flagged it as complex, with a magnetic configuration prone to flares. But it wasn't until later in the day, when space weather feeds updated, that the timing became clear. A moderate flare had occurred just before sunrise, erupting from that very region. One of the early solar models showed the ejection path, nearly radial, almost perfectly aligned with 3I, Atlas's projected vector. The image was uploaded to a local astronomy forum by lunchtime. By mid-afternoon, it had crossed into broader amateur networks, and by evening, it was making the rounds on science Reddit threads, message boards, and quiet mailing lists. The commentary was immediate. Some dismissed it, processing artifact, over-sharpened, software glitch. But others weren't so sure. The light distribution in Paul's image didn't follow typical stacking errors. The glow didn't smear, it flowed. And most importantly, it matched nothing in the official archive. NASA's Hubble image of 3 Colon Atlas from just a week earlier looked completely different. A classic blur, a soft halo, no sharp contours. James Webb data in the infrared didn't hint at any hard edges. If this was the same object, then something had changed, or something had been missed. By the end of the day, Paul Craigs wasn't alone anymore. Other backyard astronomers began posting images, not identical, but similar. A few from Chile, one from southern Italy, another from Western Australia. Different angles, slightly different setups, but the same unsettling clarity. This wasn't supposed to happen. The comet, if it was a comet, was reacting to something. Or maybe it wasn't reacting at all. Maybe it was doing something. And that thought hung in the back of Paul's mind as he reviewed the data again, frame by frame. He checked timestamps, cross-referenced solar data, checked for cosmic ray interference. Nothing explained it. Not naturally, not yet. And somewhere, not far from that same stretch of sky, sunspot AR4366 continued to grow. Its magnetic loops were twisting tighter, its flare potential rising. And 3I Colon Atlas? It was still there, still glowing, still symmetrical. Whatever was happening had just begun, and it started in a backyard with one picture on the morning of February 3rd. The forums weren't prepared. When Paul Craigs posted his image of 3I Colon Atlas to the Deep Sky review board just after noon on February 3rd, it didn't come with bold claims or cryptic warnings. Just a file name, atlas_feb3_fullstack.dng, and a caption, Dwarf 3, 12 seconds, times 110 stack, color stretch only, thoughts. But it wasn't long before the replies turned frantic. The first to comment questioned the contrast levels. The second asked for raw files. By the 10th reply, someone had already pulled it into PixInsight and ran a wavelet deconstruction. And that's when the conversation shifted from critique to disbelief. What people were seeing in Paul's image didn't fit any known comet profile. At the centre of the object was a white fuselage, solid, smooth, and far too uniform. Around it, instead of a typical fuzzy halo, there was a tightly contained blue glow, slightly asymmetric, almost like a charged field. A visual contour, not a soft gradient but something that looked deliberate. More structure than sublimation, more silhouette than smear. And it got worse, or stranger, depending on your point of view. Because alongside Paul's image, another was posted. This one from a contributor in southern Spain using a different telescope, an Unistellar EV Scope 2. Less powerful, less refined. But still, it showed the same thing, same white core, same faint blue envelope, same unnatural clarity. Comet enthusiasts were torn. Some insisted it was stacking artifacts, ghost frames, deconvolution errors. Others argued it might be lens aberration, or digital sharpening gone too far. But when Paul uploaded his raw FITS file with the metadata intact, the tone changed again. It wasn't a fake, the data checked out. That night the moderators pinned the post and the thread jumped platforms. Twitter, Discord, Reddit. Even a few fringe tech YouTubers picked it up. And while mainstream science media stayed silent, for now, amateur astrophotographers knew something unusual had just happened. Because if Paul's image was even halfway accurate, then this wasn't a comet in the traditional sense. Comets don't come out of deep space with engineered geometry. They don't form white cores with glowing sheaths, they don't stabilize under solar pressure, and they certainly don't glow brighter after a sunspot's flare. But Paul's image showed something organized, something almost crafted. And here's the thing that caught everyone's attention. Paul wasn't working with elite equipment. His Dwarf 3 was a consumer-grade telescope, portable, affordable, the kind of gear any serious hobbyist could own. It didn't have adaptive optics. It wasn't cooled. It didn't sit on a mountaintop observatory with $1 million dome. It sat on a wood deck beside a barbecue grill, and somehow it had captured an image that rivaled, even surpassed, the published outputs from Hubble or Webb, not in resolution, but in revelation. Because where the official images showed blur, Paul's showed shape. Where they showed randomness, he had found precision. By midnight, dozens more telescope users had begun scanning the same patch of sky. Some repeated the image, some didn't, and that only deepened the mystery. Why did certain scopes see the structure while others didn't? Was it angle? Timing? Processing? Or was there something variable, something dynamic, about the object itself? Whatever it was, 3I Atlas had crossed a threshold. It was no longer just the third interstellar object to visit our solar system. It had become an event, a phenomenon, a question, one that didn't have a neat answer. And as for Paul Craig's, the man who started it, he turned off his telescope just after 3 a.m., having spent the entire night responding to messages from strangers, physicists, skeptics, and a handful of aerospace engineers. He didn't know what he'd captured, but he knew what it wasn't. It wasn't noise, it wasn't dust, and it wasn't going away. While amateur astronomers were still dissecting Paul Craig's image of 3I Atlas, something else had been brewing on the surface of the Sun. Unnoticed by most, yet recorded in every solar observatory log. Active region 4366, a massive sunspot complex, had just released one of its strongest bursts to date. The flare was classified as M5.6, moderate by space weather standards, but potent enough to disrupt satellite communications had it been Earth-facing. Instead, the blast surged outward, angled along the ecliptic directly in the orbital path of the interstellar visitor now under scrutiny. Timing, as always, is everything. The flare erupted at 4:12 UTC on February 3rd, roughly 4 hours before Paul captured his image. 4 hours before a backyard telescope revealed a shape no comet should have. And while that might sound like coincidence, the physics of solar interaction doesn't dismiss timing, it studies it. The flare came from AR 4366, a region of tangled magnetic fields, wider than Jupiter, darker than the solar photosphere, and bristling with pent-up energy. AR 4366 had grown quickly over the previous 5 days, forming complex delta configurations, magnetic knots known to produce violent solar events. What made this one unusual wasn't its magnitude. It was the direction and what followed. Solar flares are often accompanied by coronal mass ejections, or CMEs, massive clouds of charged particles hurled into space at speeds exceeding 2 million kilometers per hour. AR 4366 released one, fast, focused, and oddly quiet. Solar physicists noted it in real time, flare, then ejector. But something was off. Instruments from the Solar Dynamics Observatory tracked the CME's trajectory with high confidence. It was heading outward, not toward Earth, but roughly 18 degrees off axis from our planet. In isolation, that wouldn't be notable, but that was the exact sector 3I Colon Atlas was crossing. Hours later, ground-based sensors and satellites began picking up strange data. No ionospheric disturbance on Earth, that was expected. But Stereo A, the solar probe positioned to the side of Earth's orbit, caught something else, a localized density fluctuation in the solar wind. A small compression zone, unusually sharp. Almost like a shock front had passed through a barrier, except no spacecraft was there. No magnetic object, no known reason, except 3I Colon Atlas. And if you trace the time back, the disturbance began just after the flare, just after the CME, just after the object would have been enveloped by both radiation and charged plasma. Here's the strange part. The object didn't fragment, didn't tumble, didn't even dim. In fact, multiple amateur reports described a brief surge in brightness during that time, not a flare of its own, more like a reflection, a momentary glint recorded by 3 telescopes, including one in Chile and another in Utah. The visual data showed something almost unheard of for a comet under direct solar exposure. A symmetrical increase in magnitude, a sudden shift in reflectivity, and then a return to baseline. No fragmentation, no debris, just a pulse. Theories spread fast. Some said the brightness spike was just a coincidence. Others speculated about electromagnetic coupling. If the object's surface had metallic content, maybe the CME's fields induced brief current surges. That could cause heating, reflection, or something else. But none of the official instruments, Parker Solar Probe, SOHO, or Solar Orbiter, recorded typical signs of sublimation. No jets, no mass loss, no flickering, just stability. Too much stability. That's when observers began to whisper something new. It didn't look like the object endured the flare. It looked like it responded to it. And back on the Sun, AR 4366 wasn't finished. It continued twisting, coiling, building energy, ready for the next pulse. Because this wasn't just a story about a comet, it was about a conversation between a star and something passing close enough to listen. By the time the solar data from AR 4366 finished propagating through the monitoring networks, attention had already swung back to the image that started it all. Paul Craig's photograph was no longer being treated as an anomaly. It had become a reference point. People began lining it up against everything else: Hubble imagery, James Webb infrared frames, ground-based observatories from Hawaii to Chile, and that's where the discomfort set in. Because the official images of 3I Colon Atlas did not match what the backyard telescopes were seeing. Not in detail, not in structure, not in behavior. NASA's published frames showed what astronomers expected: a diffuse coma, a soft nucleus buried in dust, light scattered in every direction. A comet behaving like a comet. Paul's image showed something else entirely. The core was not buried, it was exposed. A sharply defined white center sat at the heart of the object, surrounded by a narrow luminous envelope. The brightness fell off abruptly, not gradually. There was no classic dust gradient, no fuzzy transition from solid to gas. Instead, the light behaved as if it were reflecting off a boundary. That alone was troubling. Astronomers know how comets scatter light. The physics is well understood. Dust grains polarize sunlight, gas fluoresces, ice sublimates and creates halos that blur outward. None of those processes produce hard edges. None of them produce symmetry at this scale. Yet the symmetry was there. Independent analysts began reprocessing the data using different assumptions. They removed sharpening. They suppressed noise. They even degraded the image on purpose to see if the structure would dissolve. It didn't. The geometry persisted. The core remained crisp. The halo stayed tight. Then someone overlaid the brightness profile. In a normal comet, brightness decreases smoothly from the center outward. In Paul's image, the curve dropped sharply, plateaued briefly, then dropped again. That pattern resembled specular reflection, not diffuse emission. Light bouncing off a surface, not scattering through particles. That raised a dangerous question. What kind of surface reflects sunlight like that in deep space? Certainly not loose ice, not porous dust, not rubble. Infrared data complicated the picture further. James Webb's instruments detected carbon compounds and faint water signatures, but nothing that explained the visible brightness spike. The infrared brightness did not increase in proportion to the optical brightness. In fact, it lagged behind. That meant the light wasn't coming from heat. It wasn't glowing. It was reflecting, and reflection implies structure. At this point, the discussion split into two camps. One argued that the backyard images were misleading, that atmospheric effects or sensor quirks were exaggerating contrast. The other camp argued the opposite, that professional observatories were averaging the signal away. Large telescopes don't take pictures the way backyard scopes do. They prioritize sensitivity over immediacy, long integrations, heavy processing, algorithms designed to smooth noise and extract faint details. Those methods are excellent for studying diffuse objects, but terrible for preserving sharp, transient features. If 3i Atlas had briefly exposed a reflective geometry during or after the solar interaction, it might not survive the pipeline. A sharp signal could be treated as noise. A boundary could be averaged into blur. A structure could vanish into statistics. Paul's telescope, by contrast, had captured the moment raw. Short exposures, minimal assumptions, just photons hitting a sensor. And those photons told a story that didn't align with the official narrative. By late evening on February 3rd, as a one fact had become unavoidable. If Paul's image was accurate and there was no evidence it wasn't, then 3i Atlas was not behaving like a passive object. It had a form, it had boundaries, and those boundaries interacted with sunlight in a way no known comet ever had. This wasn't proof of anything extraordinary, but it was proof of something missing. Something our models hadn't predicted. Something our instruments weren't optimized to see. And that realization changed the question entirely. It was no longer about whether the picture was real. It was about why it existed at all. There's a reason mirrors don't belong in comet models. Comets are chaotic. They tumble, they fragment, they scatter light like dust thrown into a headlamp. Their surfaces are uneven, cratered, porous, coated in volatile ices that boil away under solar heat. And when sunlight hits them, it bounces in every direction. That's why they glow. That's why their tails form. They do not reflect like mirrors, but 3i Atlas did. After Paul Craig's image began circulating across forums and private mailing lists, researchers started examining a different kind of data, polarimetric signatures. Not colour, not heat. Just the direction in which light waves twist when they reflect off a surface. Polarimetry is subtle, almost delicate. When sunlight reflects off a rough or porous surface, the light becomes polarized, angled in a certain direction, and that polarization tells you something about the surface it touched. Dust scatters light in one way. Smooth reflective materials do it differently, and in the case of 3i Atlas, the data pointed squarely at something rare. A polarimetric profile that didn't fit any known comet. One study, quietly released in late January, had already flagged the anomaly. A deep negative polarization branch, sharper than what had ever been measured on a natural comet. At phase angles where comets should polarize light slightly to the left, 3i Atlas was polarizing it sharply to the right. The inversion angle was shifted, the magnitude was higher, and the result was clear. This object wasn't diffusing sunlight, it was redirecting it. One scientist described the effect this way. It's as if the surface isn't covered in dust, but in something dense, smooth at the microscopic level, something that reflects light with directionality, like brushed metal or polished glass. Not something you say lightly about a comet. Even more confusing, this reflection was stable. It didn't shimmer, it didn't break up. Multiple polarimetric scans across different nights showed the same angles, the same intensity, the same mirrored behavior. That's not how comets behave. In fact, nothing natural in our catalogue behaves this way. Not icy moons, not asteroids, not even metallic meteorites. Every known surface in the solar system scatters. This one was reflecting, and the implications were immediate. because a surface that reflects in such a coherent way must have order. Not in a visual sense, but in structure. The particles must be uniform, the geometry must be consistent. You don't get mirror-like behaviour from random rubble. And yet, that's what comets are. Rubble. Dirty snowballs from the edge of a solar system. But 3I Atlas had arrived from beyond. Interstellar space is not kind to loose material. Radiation, or micrometeoroid impacts, cosmic rays, over millions of years, any fragile surface would be pulverized, shredded, turned to dust. But a dense, compact structure, one with uniform composition, maybe even self-repairing surface layers, that might survive, and that might reflect. So if this object truly was mirroring sunlight, redirecting photons like a polished hull, then it wasn't just different, it was designed differently, shaped perhaps, hardened, built to last. Still, scientists hesitated. Maybe the coma had momentarily collapsed, revealing a smoother than usual surface. Maybe the light curve was skewed by background stars. Maybe the dust was just behaving oddly. But the numbers didn't lie. The reflection wasn't ambient, it was specular. It didn't wash across the sky. It moved with the object. Sharp, clean, predictable. That word again, predictable. Not something we associate with interstellar debris. It raised a possibility no one wanted to speak aloud just yet. What if this object wasn't passively reflecting sunlight, but using it? A mirror, yes, but not a mirror for viewing. A mirror for motion. Because the next thing scientists would realize, the thing Paul Craigs had unknowingly photographed wasn't just a reflection. It was a reaction. And that changed everything.